Welcome back. Previously, we looked at the numerical representation of images. Now we're going to introduce convolution and the benefits it provides in keeping our model from having too many parameters, at the same time extracting important features. Let's recall what exactly the neuron does from our previous video. What we have is a function that takes an input and multiplies it by some weights, then carries out an activation on the output of the function. This results in a value that we can then compare to a threshold to let us classify our output. This is essentially our logistics regression model. What we've done so far is take our neurons and put them into a dense network. In the image that we have, the yellow circles are our input features. The green circles are neurons in dense layers. What that means is every neuron in one layer is connected to every neuron in the subsequent layer. This is a dense network architecture. The hidden layers represented by the green circles and our output layer is represented by our red circles. So this is the dense network architecture. In a convolutional neural network, we do not have that dense architecture. Instead, what we have is something called the convolution, and what we see is unlike the previous diagram. In here, we have blue circles which represent convolution layers. We still have a dense layer towards the end, in our output layer. With the convolution layers, what you see is the input, which is presented by the yellow circle, and it's connected to some neurons in the subsequent layer, but not all neurons. In a convolutional, the output is connected to some neurons in the subsequent layer. We continue to do this until we get close to our output, where we then have a dense layer, one or more dense layers, and our output. What the dense layers do is to finally learn to extract the features that we have learned by previous layers, then perform the classification. The convolution operation itself is a mathematical operation. What we have is represented on the screen. On the left side, we have this matrix which represents one layer of our image. So if we had a color image with 3 layers, this would be one of the layers. Recall that from our image representation. The pixels have a numeric value from 0 to 25. What the convolution operation does is it introduces a sliding window called the kernel. And that's represented by the red box on the right. The essence of that kernel is to perform some sort of operation. It could be a sharpening operation. It could be a smoothing. It could be an operation in which you try to find a certain feature within that window. For example, is there a curve or a horizontal line? Or is that a vertical line? What happens during convolution is that this kernel or window, which is represented in red, starts at the top left of the image, then it slides across the image slowly, and it performs an arithmetic operation and yields an output. And we could see what that is on the screen, where we have all the multiplications and additions, which is essentially a dot product. The kernel itself has a size. In this case, what we have is a window that is 3 pixels wide and 3 pixels high, and it's a common dimension. We also have the concept of a stride, which is how many pixels we slide across, where we move our window. A lot of the time, we slide by 1 pixel. There's also the notion of padding, which is if you look at the image on the screen and the kernel by the arithmetic operation on the inputs, the dimensions of our output will be different from the dimensions of our output. So padding exists, so that if you would like to have your output be in the same dimension as your input, you could introduce padding. What padding does is it adds zeros around the image, such that the window is then able to go outside of the normal boundaries of the image, then produce an output that is the same dimension as the input. Let's recap some keywords. There's a kernel, which is a small matrix that is used to apply an effect, and what we saw in our example was a 3x3 kernel. There's stride, which is a number of pixels that we move our kernel by. There's padding, which is whether or not we add pixels with 0 values around our image, so that our output is the same size as input. That's a lot of mathematical operation that goes on with convolution. As a result, we have some convolution layers that have been implemented in TensorFlow. Examples of these are a 1D convolution, which is called a conv1D, which only slides horizontally. This is typically not applied to images. It's applied to other types of unstructured data, like sound and text. Then we have what's called a conv2D, which is what we're going to be looking at here. There's also conv3D. When we implement conv2D, we need to pass in certain parameters. First parameter is the filters. The filters are the dimensionality of the output space. We'll get to that later. There's also kernel size, which is the height and width of the 2D convolution. In the image that we saw that was 3 by 3, we also need to specify our strides, which is how many pixels will move the kernel across. Then padding, which is usually valid, or the same depending on whether we want an output that is the same dimension as the input. Finally, we can also have activation, which is what sort of activation we would like to have applied to our outputs. If we don't specify an activation, it's simply a linear activation. Let's take a look at our notebook and see how we'll implement convolution to get started. Let's install TensorFlow and import all the modules that we need. We're not going to train our models. We're simply going to define the models. Then look at the summary of the models. First thing we do is create a dense model. And because the data that we've imported is small and size 28 by 28 pixels, we introduce a flattened layer where we specify the input shape of 28 by 28. We then add 2 dense layers with 784 neurons per layer. We're going to leave out the output layer, in this case, because we're not training the model. Once we look at the model summary, we were able to see the various layers that we have and the parameters that we have. We could see that our dense model already has 1.2 million parameters. Next, we'll introduce a convolutional model, and we define it using a sequential model. In this case, add convolutional layers instead of dense layers. And to keep the comparison the same, we add 2 convolutional layers. Now, a convolutional layer has to be followed by a pooling layer. So add the pooling layers just to keep everything working well. We'll discuss pooling in a later video. When we add our convolution layer, we specify our filters, which is 32. Our kernel, which is 3 by 3. We specify an activation, and for the first convolutional layer, we specify our input shape so that it's able to flatten the image for us. Now notice that our input shape specifies the width and height of the image, as well as the number of channels. We use the same number of kernels in both layers. We make use of 32 filters in the first layer, 64 in the second. When we look at our model summary, we see that we have only 18,000 parameters. This is small. What it means is that the number of computations that we'll be carrying out will be much less than a similar computation with a dense layer. In the next video, we're going to look at pooling.